here and that I have got the chance to give some of my ideas or my point of view on optimal design. And in contrast to the talks we have heard before, it's more on regression design than on design for certain analysis of variance models, but it might be also applied in there. So in fact, those who attended the series of lectures 3 weeks ago, it's like 3 years, might get out now because there's nothing new, probably. Anyway, might be some interesting review anyway. So what I started off were some problems coming from applications, and I just want to start with these examples, but just give a short outline. So I will briefly, very briefly say something about fixed effect models. I will define what the information is. I will just state what the design is, which is just 1 or 2 transparencies, and then I will focus on linearization and at the final end on mixed models. So this is for nonlinearity, and this is for the mixed effect things. And you will find out that there are a lot of problems and there are hardly any solutions. So I would be very happy if at the end of my talk somebody could get up and say, oh, everything has been solved 50 years ago in some paper of the Pedagogical Institute. Well, where does it come from? I will give 2 introductory examples. One is from pharmacokinetics, some project with the pharmaceutical industry, and the interest is in such kind of curves, nonlinear one, which measures the concentration of a drug in the body or in blood over time. And one might be interested in some characteristics of that, like the area under the curve, which says something about bioavailability. Don't ask me what this is, but this sounds impressive. And so that we have one individual over here, and it has this curve. But in fact, there are many individuals, and fortunately, people are not all equal. They are different, so each individual has its own curve. So we have some effect in there, and this is somehow related to some, I will relate it to a superpopulation model, so we have some random effect in there. Second example, and this is the transparency where you might recognize that I have done at least one thing during the last 2 weeks. So I've changed it slightly. Look for the third alternative you can choose from. This is a conjoint analysis model, and it's based on some question, some project which has been posed by the Bavarian Ministry of Agriculture concerning some difficult to see, concerning the effect of some small signs on the bottles stating that this is coming from Bavaria or from the European Union or whatever. In a way, I'm cheating because the right bottle probably is not allowed to be sold in Germany. And the interest is in measuring the utility of whatever certain attributes, for example, these small signs, where they influence the consumer behavior or marketing decisions and so on. And there's one individual down there, but you might guess that this is not the only individual which is asked, and we want to know something about the utility function which is described here, which might be described by some nonlinear model or generalized linear model. We have to take into account that there are different individuals, so each individual has its own curve, and we have to measure across the individuals, or we might be also interested in the individual effects. So I don't want to go into detail for these examples, but this is just for motivation. Okay, what's a fixed effect model? Just start off, we have a lot of things in there, just some notation. We have some observations, usually known by Y. We have some explanatory variables, which are, for example, the time points at which we are measuring the concentration, or which are, for example, the different alternatives we present. We have a response function which will give us the effect of this explanatory variable on the outcome, and there will be some unknown parameters which we are interested in, and as we are doing statistics, there will be random errors somewhere around. And for simplicity, I will mostly assume that we have homoscedastic errors and things are independent and don't have to care about further difficulties occurring. So, and there will be a simple example which we will approach several times. We just look for a very, very simple nonlinear example which might be either completely nonlinear or a generalized linear model with exponential decay. And the question is, here we would be interested in this decay factor beta. Well, start with a linear model, that's what everybody knows. So if you rewrite the response in the way that this mean response mu can be split up in sum of regression functions f1 to fp weighted with the unknown parameters, then it looks like that, and theory is well developed, so don't have to care much about that. And you know from standard linear algebra courses, you can linear model courses, you can rewrite this in vector notation, and essentially the influence of the explanatory variables, and those are those things which we can choose and which will be our design later on. They are down here in this information matrix. Well, okay, and then can do some estimation. So if you want to estimate this parameter in there, one dimension, of course, it's easier. We have to write down these equations. Normal theory, this is maximum likelihood. And what is more important, we are interested in this matrix F transpose F, which is proportional to the inverse of the covariance of this estimator. So for quality reasons, we want to make the covariance as small as possible, which means that we want to make the information as large as possible. So that's standard things, but just to have the notation at hand. And if the variance, so I tacitly assumed, and I've further on will mainly tacitly assume that the variance is unknown, that it is known. But if it is unknown, then the information becomes a little bit more difficult, but only a little bit. In the very end, there's no difference because we have this nice block diagonal structure. So the information for the location parameter beta, which we're interested in, is not affected by where we know the variability of the error terms or not, as long as they are homoscedastic. You'll see short examples later on that in our cases it might well be a problem. Okay, now nonlinear models looks much more complicated. We don't know the structure of the mean response, and just to notice, the information must be based on the asymptotic covariance matrix or something similar asymptotic information matrix, but which should measure the asymptotic covariance in a sense. And what is essential is which kind of estimator we are going to use, because it's in nonlinear models it's not so clear at all. We can use maximum likelihood. This will be asymptotically efficient, and we have some theory about that, but this estimate is not always, this estimate is not always feasible. So there are alternatives like weighted least squares, quasi-likelihood, or generally speaking, generalized estimation equations, which might result in different asymptotic covariance matrices, and which might result in various different design criteria and hence different optimal design. So the design in nonlinear cases usually has been tailor-made for the estimation procedure which is chosen. Okay, what is the design? The design is just a setting of the explanatory variables. So if we can make n experiments, we just choose n different settings from a certain design region, and the corresponding information can be this is the F transpose F, or we can rewrite it as the sum of the information given by the individual observations, individual settings. And this makes things usually easier. And the aim is that we want to choose the experimental settings or the explanatory variables in such a sense that the covariance becomes small, or saying the inverse of the information becomes small, the information itself becomes large. Well, all functions thereof. I don't want to discuss all this DA, whatever criteria. The examples will be much easier. Okay, so now we come to the more difficult things, how to get this asymptotic variance covariance matrix, or the asymptotic information. And the usual approach is to make some linearization, take a Taylor expansion at some specified value beta naught, some initial guess. And this is a problem. This has to be some prior information to put in there, but we'll do it at the moment, and one might to discuss the appropriate choice. If you do that, you find out in a way that you get something like a linear model. If you rewrite these things in a certain way, you get some constants, and you get something which is linear in the betas up there, and the derivatives of the function of the mean response function with respect to the parameters will be considered as the corresponding regression functions. But the problem is the linearized regression functions depend on the choice of the point where we take our linearization. So if we take a linearization at a different beta naught, then we will get different regression functions, and then the information matrix will become different, and probably the designs will also be dependent on that. And then the trick is that we assume that this point where we do our linearization is in fact the true value, which we are going to estimate, which we don't know, but we start with some prior information, and we hope that everything works perfect. So this is just pure heuristic doing this linearization. And I want to give some feeling that it is not so bad as it might look at its first glance. Okay, start with homoscedastic errors. So we have this model. I suppressed this beta naught, so I'm assuming that I've got the linearization at the true parameter. And the information matrix then just rewritten. You can see what I already mentioned. It depends on the unknown parameter beta, but it looks just the same as before. And the optimal design will also depend on beta, and I will only speak about local optimality here, but you can think about weighted criteria and so on. But this is another level of making things even more difficult. Simple example, get this exponential decay. If you linearize that, you get this linearized model where this is a derivative with respect to the parameter, and the information, which is a 1-by-1 matrix, is just the sum over x squared times e to the minus 2 beta x. And this is optimized there where this function attains its maximum. So you find out the optimal design will be that all observations are to be taken at 1 over the parameter to be estimated. Okay, and if you have a good prior, then this is fine. But anyway, it is sensitive, and it depends on the unknown parameter. So taking heteroscedastic errors, and things become more difficult. The information matrix has to be weighted by the inverse of the variance in here. So there's another dependence on the unknown parameter. And look for a simple example, and I just assume that the variance is proportional to the mean. which might be a considerable assumption or not. And if you do it like that, then you rewrite this information. You get this form. It's x squared times e to the minus beta x. And if you maximize that, you will find out you must put your observation a little bit farther out. So the optimal design will be take all observations at 2 over beta. So far, so good. We make it a little bit more complicated or more easy. Consider normal theory. And question still is normal normal? We have some more structures, so we can not only get this linear information matrix, but we can take the Fisher information matrix getting via the score functions for the maximum likelihood estimates. And as in linearization, if we have homoscedastic error, we get the same result, not very surprisingly. And so the maximum likelihood estimate will be asymptotically normal. The asymptotic covariance is just proportional to the inverse of this information matrix. So everything is fine here. So our example, so everything goes through. Don't have to look more carefully. So it works out. So now heteroscedastic error, and some curiosity occurs that we can now get additional information from if we know the function of the variability and if this depends on the same set of parameters. In this case, the Fisher information matrix is increased by a positive term which includes, in this simple case, the information from the variation. So this is the information from the location parameters. Oh, the lambda should be sigma to the minus 2. Well, and we get some information from the variation. So what will this do to our example? Okay, just look asymptotic normality. If you take maximum likelihood, then you will find out that everything is okay with this information matrix. The maximum likelihood will be asymptotically normal with asymptotic variance covariance matrix proportional to this information matrix with additional terms coming from the heteroscedasticity. If you take something like weighted least squares or generalized least squares, you will end up with a variance covariance matrix which is proportional to the information without this knowledge. So that's what one usually would optimize. Okay, so our example here, normal errors, heteroscedastic variance proportional or exactly equal to the mean. Then we get this information or information matrix, the term from the linearization, the term from the variability. And I don't show you how the maximum likelihood estimate looks like. It looks, at least I wouldn't recommend it to a practitioner. Anyway, if you do that, you get the optimal design, pushing your explanatory settings for the explanatory variable as far outside as possible. Because which is in a way contradictory. So this comes from the second term, which says we get most information there where the variability is very flat. Okay, don't know what it means. Maybe somebody can explain it. Well, and if we have some additional unknown parameters in there in the variance, then things become even more complicated. We have to write down the full Fisher information matrix, incorporating both parameters, the location parameter and the additional variance term, which gives such a block matrix where m beta belongs to the information, to the location term, and the theta index indicates this variation term. And the unfortunate thing now is that the off-diagonal elements or blocks are not equal to 0. So we get additional terms in there, which means that the information matrix, if you look for just for the location parameters, gets a slightly more complicated form. So we have to subtract something. Just to look for our example, so if we state that same example as before, but we have now an additional proportionality factor for the variance incorporated there, and then the information looks like that. You get an additional term over here with a negative sign, and the optimal design now is a little bit more complicated. Essentially, you should take half of the observation at 0. You don't get any information about the location parameter, and you should take the other half as large as possible. Well, at least theoretically interesting result. Okay, so this is some problems which occur with nonlinearity, and we will have even more problems if we have random effects in there. So what is the outcome, the model specification here? We have observations, and it looks like before, but now the parameters are individual dependent. So the BIs have an index I coming from each individual. So if we look for this exponential, each individual has different curve, and usually we assume something like normality. So here individual parameters are normally distributed, so the error terms should be normally, to keep things as simple as possible in the hope that normal is normal. And we are interested in the population parameters. We might be also interested in the variance components, but this is still more difficult. Okay, so the linear mixed model can be easily written like that, split up, or one type of linear mixed model, split up the individual, the effect in the fixed effect and in the random effect, and then look for the parts. So the individual covariance matrix now introduces some correlations coming within the individuals, which can be written down like that. And you see that the design also occurs within the variance structure or covariance structure. And the information matrix then becomes a little bit more complicated, but so we have to add up the information from all individuals, and for each individual of the information which is of the form design matrix transpose inverse of the variance covariance matrix times design matrix, and this is proportional to the inverse of the covariance. Sorry for that. And in fact, we get already here the dependence on a parameter. We get the dependence on the specification of the variability of the location parameters. Okay, linearization. So this is a typical linearization as it has been used, pure heuristics. So we do the same thing as before. We linearize our nonlinear outcome, and we get this linearized regression functions times the parameters, linearized regression functions times the random effect, and some additional errors. And this looks quite good. And if you then transform the data, you get some linearized model in there. And the linearization is taken at a fixed point beta naught. And then to compare that, a refinement had occurred approximately 5 years ago in the literature, which says we should take our linearization, or as I understand this, takes the linearization as a true parameter, then it looks quite the same. But the question is, what is this? And the regression function depends on the unknown parameters. And this looks, in a way, it looks appealing, but it causes some additional problems. And I hope I have the stop. I have the time to come just to the conclusion. The quick and easy heuristics. Skip that, the simple example. Okay, where's the conclusion? The conclusion is down there. You just should forget about this second approach. So there is no heterogeneity which is caused by the nonlinearity. But this is so far a conjecture.
Have a couple of minutes for questions.
Just a comment that models arising under stochastic frontier models, design problems arising, I think throw up other similar problems. Helen had a poster this morning where there are dependence and extra variance terms. And I realised there's something with mixed models.
Yeah. What is true, if you have heteroscedasticity in there, which is not coming from the nonlinearity, but which is intrinsic, then this will cause additional terms. So the message should only be if, so there's no heterogeneity which is induced by the nonlinearity, which comes from the fact that you have regression functions which depend on the unknown parameter beta. Because after you have specified your point of development of your Taylor expansion, then it is fixed, and you should not fiddle around with it.
Other questions?
With what should, yes, I suppose, with what should you not fiddle around? I mean, unclear. You've got a sigma x squared at some point. You're saying that shouldn't be there? About 15 slides back, but it's too late. Right?
No. So, okay, that's a linearized model. So the essential thing is that I have to fix the beta here, the development of the where I take my hyperplane to the space of regression functions and changing this. So I should not have a dependence in here on the beta. So I just have to fix that. And the basic idea behind that is that you, if you would observe the error terms, then this would immediately disappear. So not observing the pure error terms should not give more information than if you observe them.
Let's thank our speaker again.